Okay, the next unit is impulse and momentum. Recall Newton's second law. Net force is equal to mass times acceleration. Recall the definition of acceleration that Galileo gave us. Final velocity minus the original velocity divided by the time. So we're combining Newton's second law with Galileo's definition of acceleration. What I'm going to do next is multiply both sides by time, both sides of this equation by time. And I get this expression. The next thing I'm going to do is multiply both through by mass. So I get m df minus m do equals sigma f delta t. Now I'm going to rewrite this up here because this is the equation of the hour. Okay, so here we have the equation of the hour. This is known as the impulse momentum theorem. This term here we call momentum, and since there's a subscript f there, we call it final momentum, or PF. This term here would be the original momentum. So we have a change in momentum, final minus original, which could be rewritten as delta P. On this side, we have a term which is called impulse. Okay, and again, the P here is momentum. And the delta means change. So an impulse causes a change in momentum. So you can have a change in momentum if the velocity of an object changes, but you can also have a change in momentum if the mass of the object changes. So in other words, it doesn't have to be just a change in velocity. You could also have a change in mass. Okay, so keep that in mind. For example, a rocket, okay, the mass of the rocket changes as it takes off. That's a change in momentum. Okay, but right now we're just going to take a look at the case where the velocity changes. So the momentum change is due to a velocity change rather than a mass change, at least right now. Okay, so let's look at some illustrations of this. I would say one of the most important ones is its application to seat belts and airbags in cars. Okay, let me explain. Okay, so suppose we have a wall here, brick wall, let's say. And a car comes along at a speed v, car has a mass m. So its momentum, we could say, is mv. The car strikes the wall, and let's say it comes to a stop eventually. Okay, so it comes to a stop. So how did that happen? Well, during the collision, there was a force on the car, and that force, of course, occurred over a time t. So if we would extend the time over which the car stops, so like having the car crumble, for example, have a bumper on the front of the car that absorbs the shock and the car crumbles. So if we would extend the time over which the car stops, what that would do is reduce automatically the force which is applied to the car to stop. Why? Well, because remember, this quantity here is equal to the change in momentum of the car. And isn't the change in momentum of the car independent of how long it takes that change to occur? Right? Delta P is equal to the mass of the car times the final velocity of the car minus the mass of the car times the original velocity of the car. So the final velocity of the car is 0. It stops. So all that's important is the original velocity and the mass of the car. And that's independent of the time. So by extending the time of the collision, you reduce the force. And then inside the car, you can also help, right, by having an airbag that extends the time over which the passenger comes to a stop. So there's a seat belt. So that's a good example. Now I would like to take a look at bounce versus no bounce. So suppose we have a car, again, traveling toward a wall with a speed VO, hits the wall, it experiences an impulse, force times time, and it doesn't bounce. Okay, so it comes to a complete stop due to this impulse. And we're going to compare that to this scenario where a similar car comes along at a speed VO, hits the wall, experiences an impulse, but then bounces away from the wall at a speed VF. So what we're going to do is compare the two impulses, and what we're going to see is that the impulse here is greater than the impulse here. So when things bounce, more impulse is imparted, greater change in momentum is imparted. And this explains why the paddles of kayaks, for example, are curved. It explains why they design cars so that they don't bounce in collisions. They collapse and come to a stop as quickly as possible. Well, I guess you wouldn't want to say quickly as possible, but you definitely don't want them to bounce. So they should come to a stop due to the crumble zones. And the people in the car should come to a stop over a period of time due to the airbag and the seat belts. It also helps you understand why, if you're falling, when you hit the ground, you should hit the ground and bend your legs and come to a stop. Don't hit the ground and keep your legs stiff. It also explains why parachuters, when they come in, they'll come in and they start running and slowing down to a stop. Okay, so let's see why you get a bigger impulse here. So over here, car comes in. Okay, so it hits the wall. So it has an original momentum, right, MVO, and then it comes to a complete stop. So the change in momentum would just be negative M, right, the mass of the car, times the original velocity, right? Because the change in momentum is mvf minus mvo, and since the final velocity is 0, the change in momentum is just negative mvo. Right? So this is the change in momentum of this car during that collision. Okay, over here, car comes in, has a momentum mvo, and then it bounces and it goes back to the left, okay, the opposite direction. So it has momentum mvf. So the change in momentum is going to be mvf minus VO. But VF is to the left. So VF is in the negative direction. So what we end up with is negative M times VF plus VO. And you can see that this quantity is larger than that quantity. Now keep in mind that the negative sign indicates direction, not size. So this is definitely a larger change in momentum than here. Therefore, a larger impulse here than here. Okay, let's do a little demonstration. Okay, so we're going to make believe that this is a person in this parked car, and this car comes along and strikes that car. Let's see what happens to the person. You notice that this car bounced away. Right? This car came along, hit that car, and it bounced, and the person fell out of the car. Now what I'm going to do is I'm going to turn this car around. So now when it hits the parked car, they stick together, so there is no bounce. And let's see what happens to the person. Okay? So that kind of shows that no bounce is better than bounce. Recall the demonstration I did with the cart that had a fan attached to it and a sail. And what we were showing is that that arrangement that Wile E. Coyote had in one of the Roadrunner cartoons was not a very good design. And you recall that I tested that, okay, in class. Now, let's go back to that, and this time what we're going to do is instead of having a flat plate, I'm going to bend it. Actually, more like what you saw in the cartoon, right? There was a sail. Well, if the barrier that I had in that previous demonstration had a bend to it, the air would bounce off of it. So you would actually get a bigger impulse in one direction versus the other direction, and it would actually accelerate. However, if you took off the barrier, the sail, it would work better. Okay, so again, the original demonstration showed a barrier like this with a fan. And we saw that the fan pushed the air hit the sail, exerted a force on the sail that way. But coming back here, as the air is pushed away from the fan blade, it exerts a force back. So these two forces are destructive and minimizes the effect of having the fan because of that sail there. But if you make this sail or barrier curved like this, sort of the way it was in the cartoon actually, now when the air hits this, it's going to bounce, and that will impart a greater impulse than if this were flat. Thus, you would get an acceleration to the left. But again, it isn't more efficient than not having a sail at all. Okay, so if you had this design without a sail, you turn the fan around, that would be the best way to get it to accelerate to the left. You might have heard of reverse thrust on jets. Okay, basically what a reverse thruster is like this curved sail. So when a jet plane lands, okay, the engines are still firing, right? So you still have the thrust, but these two, they call them clamshells, come out, and what that does is it allows the exhaust to bounce, okay, and that imparts an impulse backwards on the plane, which exceeds the forward impulse due to the thrust. Let's talk a little bit about the impulse momentum theorem when you drop something. Okay, so when I drop this apple, there's a force acting on the apple downward, and that acts on the apple over a period of time, t. But the Earth experiences an upward force of same magnitude as the downward force on the apple. They're gravitational forces. And those two forces occur over exactly the same time. So that means that the impulse on the falling apple is the same in value, magnitude, as the impulse on the Earth, which is directed upward. So that means that both the Earth and the apple undergo the same change in momentum, but in opposite directions. So that's kind of interesting. What I would like to discuss next is conservation of linear momentum. In any collision or any explosion, if the impulses are internal, momentum is conserved. And we can see that from the impulse momentum theorem, which you would call states that sigma f t equals delta p. So if the net force, net impulse, if you multiply by t, is equal to 0, then the change in momentum is equal to 0, which means that the original momentum is equal to the final momentum. So for example, with these two carts here, if this cart comes along, exerts an impulse on this cart from Newton's third law, this cart will exert an impulse back. So the change in momentum of this cart should be equal to the negative change of this cart. In other words, the momentum before is equal to the momentum after. Right? Momentum before is equal to the momentum after. Let's say you have a collision where the two carts stick together. So here you have the momentum before. Afterwards, you would have to have the same momentum. So let's see if we can predict the speed of these two carts after the collision. So we have the one cart coming in, m, multiplied by its velocity. So that's the momentum before. Afterwards, the two cars stick together. So we have 2m, because they're the same mass, multiplied by their final speed. So you can see that the final speed of the two carts together is going to be half the original speed of the first cart. Okay, now we don't have a means of actually measuring this, so other than just looking at it conceptually. Okay, let's take a look at the case where you have a collision, a head-on collision, and they come in at the same speed. Well, the momentum of this one, let's say, is mvo that way. momentum of this one is MVO the opposite way. Well, if you add those two momenta together, you should get 0. So that means that after the collision, you should have 0 momentum. Let's see. There you go. Now suppose we double the mass of this car, and we have a collision between these 3 carts. Okay, let's see if we can predict the speed of the 3 carts joined together after the collision. So before the collision, we have MVO. This cart's going to move along and strike those 2. So after the collision, we now have 3mVF. So can you see that the final velocity of the 3 carts stuck together would be 1/3 the original velocity. Okay. Let's now take a look at the case of an explosion. Okay, suppose we have 2 carts of equal mass and they're at rest, and there's a spring-loaded bumper between them. So we start out with 0 linear momentum. When I push this button here, the spring-loaded bumper is going to push on this cart, and from Newton's 3rd law, you'll get an impulse back on this cart, which is equal and opposite to the impulse on this cart. And the momentum after should be 0. Let's try. Okay. So you have this one going the opposite direction as that. So their momenta are equal but oppositely directed.